Hello students, I hope you all are doing good and are working upon the video lectures which are already circulated on the topic of Bernoulli's and binomial distribution. Okay, in this video lecture we are going to see the next distribution which is also in the discrete sense, or which I should say it is the discrete distribution or the distribution with respect to discrete random variable. The name of the distribution is Poisson distribution. Okay, so what is basically Poisson distribution? Poisson distribution is a limiting case of binomial distribution under the following conditions. So if you have completely understood what is binomial distribution, Poisson distribution is nothing for you. Okay, so before starting or before listening to this video lecture, it is better to get your basics right using the previous video lectures of binomial distributions. We have studied binomial distribution in 4 small parts through 4 small video lectures. So it is better to understand those first binomial distribution, then only come to this, because anyway you are not going to understand anything if you are not thorough with binomial distribution. Okay, so the prerequisite for Poisson distribution is binomial distribution. Poisson distribution is a limiting case of binomial distribution under the following conditions. Okay, what is first condition? The number of trials should be infinitely large, that is as n tends to infinity. Like I told you, we have taken one example of tossing a coin 10 times. So instead of 10 times, if it is 100 times, 500 times, 1000 times, then that particular question could have come under the category of Poisson distribution. This is first condition. The number of trials should be infinitely large. We have to perform experiment infinitely large number of times. Okay. Second is the probability of success, which was denoted by P, for each trial should be very small. Here in Poisson distribution, when we should use Poisson distribution when the number of trials is large from point number 1, and from point number 2 if the probability of success is very small. That means out of 1000 trials, if I am getting success 2 times or 3 times or maybe 4 times, which is comparatively very small number as compared to the domain size, then I should say this particular problem comes under the category of Poisson distribution. Okay. Third thing is NP. N is number of trials, P is probability of success. When you multiply them both is equals to some lambda, say, should be finite, where lambda is a constant. So NP should come finite, and that NP is going to play a very important role as far as other aspects of this distribution is concerned, including mean, variance, etc. Okay, so I have stated that Poisson distribution is the special case or limiting case of binomial distribution. But I should tell how this Poisson distribution is coming. What is the probability distribution formula for Poisson distribution? Like we have in binomial distribution, this formula, binomial distribution is probability of x, probability at x is equals to x, where capital X is the random variable, small x is the probability that we are talking about, probability at that point is x, is given by ncx, p to the power x, q to the power n minus x. Okay, in the previous notation I have used the symbol of bracket for showing combination, right? Right. We have used some different notation last time, but we were reading this combination. This is the combination notation. This is the underline notation is the combination notation. Previously, we used to write it as in this way, nx in the bracket. Okay, which is nothing but in the new sense now ncx, and whose formula is, as you must be aware, that n factorial upon x factorial into n minus x ka whole factorial. Okay, so this is the formula for combination. I hope you are aware of this formula. Okay, so Poisson binomial distribution is given by this formula, ncx p power x q to the power n minus x, which can be written as this, ncx p by q whole to the power x. Yes, I can always write, because q to the power n minus x can be written as q to the power n upon q to the power x. Hence this, and we know q is equals to 1 minus p, that q is probability of failure. So writing everything in terms of p here in this formula, and putting p is equals to lambda by n. Why? Because we have already stated in the third point that np is equals to lambda. We are going to take some lambda, some constant. That lambda is going to play a role here, right? So when you substitute all this, when you substitute p is equals to this thing, and when you open up this combination sign, as I told, because formula is n factorial upon x factorial into n minus x का factorial. So इस formula से अगर आप open करेंगे, so you are going to get this particular thing in this step. Okay, then it is just the matter of writing everything in terms of this lambda by n, lambda by n, lambda by x. All right. So when you do so, you will come to one point. You just verify these steps. Okay, you will come to this point where you will be having this particular term here, infinite number of terms here in multiplication upon x factorial, lambda to the power x into 1 minus lambda, this thing. Now I am worried about this term and these individual terms which are here. Okay, so left hand side we have p at x is equals to x. Yes, no problem. We know that limit, we know the one formula, standard formula in limits from your 12th standard knowledge. Limit as n tends to infinity, 1 minus lambda by n whole to the power n minus x is coming out to be e to the power minus lambda. Yes, this is the standard result. Also, limit as n tends to infinity, 1 minus 1 by n is coming out to be 1, that you know. Also, limit as n tends to infinity, 1 minus 2 by n will also know is going to be 1, because the 1 by n term or 2 by n term or 3 by n term or 100 by n term is not going to play the role, because n is going to infinity. Ultimately that thing is going to be 0. So we have 1 here. So what will happen to all these terms here? This term, this term, this term, they all are going to 1. So 1 into 1 into 1, this numerator is going to, everything is going to be 1, and as far as this term is concerned, we are going to get e to the power minus lambda there. So what is final product? P taking limits on both sides as n tends to infinity. Because why this step? Why this step? Because we are in Poisson distribution where n is tending to infinity, where the number of trials should be large. That is the center line, that is the major line. Okay, that is why we are taking the limit as n tends to infinity. Hence we get probability of x is equals to x is equals to lambda to the power x e power minus lambda upon x factorial. X is equals to 0, 1, 2, 3 and so on up to infinity. Yes, important. Okay, up to infinity we are going here, unlike in the case of binomial distribution. Right? Fine. Okay, so let us formally define this Poisson distribution. A random variable x is said to follow Poisson distribution if the probability of x is given by probability of x is equals to x is equals to small p of x equals to e power minus lambda into lambda to the power x upon x factorial, where lambda is equals to n into p. X is equals to 0, 1, 2, 3 and so on, where lambda is called as the parameter of distribution. Okay, so this is the formula which we are going to be used, in every example, I should say. Okay, what are the examples of Poisson distribution then? Examples of Poisson distributions are, let us see first example, number of defective bulbs produced by a reputed company. Okay, if some company is there and they are producing some bulbs, so how many number of defective bulbs they will be producing? A good company. Okay, when I am saying company, reputed company they are saying. Okay, reputed company. So obviously the number of defective bulbs as compared to the total number of bulbs they are producing is going to be very less. That means the probability of success here, the bulb being defective is a success for the probability finder, like for a mathematician like us. Okay, so here this example comes under the Poisson distribution, because production, the number of produced bulbs is more and the number of defective bulbs are very less as compared to that. Second thing is number of telephone calls per minute at switchboard. Yeah, it is also going to be very less. Number of cars passing a certain point in 1 minute. Number of cars passing a certain point in 1 minute. A particular point if we are fixing, number of cars will be very less. Number of printing mistakes per page in a large text. Yeah, good. So suppose I have 2000 pages, one book of 2000 pages. Okay, so and if I have 25 total mistakes in the whole book, which is very less, so probability of success is very less. The number of mistakes, the number of printing mistakes in a book of 2000 pages, if it is coming out to be 25, It is very less. So this is again example of Poisson distribution. Number of person born blind per year in a large city. In 1 year, number of person which are born blind, okay, the number is going to be very less. All right. So all these are examples of Poisson distribution. All right. So let us see what are the conditions of Poisson distribution. Poisson distribution holds under the following conditions. First is the random variable x should be discrete. That we know because it is a discrete random variable. The number of trials n is very large. The probability of success p is very small, very close to 0 in fact. Lambda is equals to np is finite. The occurrence are rare. Okay, so if the event is rarely occurring, then it comes under the Poisson distribution. All right. Let us discuss the constants of Poisson distribution, starting with mean. What is mean of Poisson distribution, or what is mean of any discrete distribution? It is summation of x into px is ranging from x is equals to 0 to infinity, because the number of trials are infinite. So x is equals to 0 to infinity x into px. Okay, so it is nothing but x into e to the power minus lambda, lambda to the power x upon x factorial. It is just the matter of simplifying the things. I am not going to simplify it for you. I am going to circulate this PDF to you, and you are supposed to solve by this your own. So what mean you are getting, the end result is useful. The end result I am concerned about. The mean is coming out to be lambda. That means mean is equals to n into p. Is that clear? So mean of Poisson distribution is lambda, and what is lambda? Lambda is equals to np. Okay, n is number of trials, p is probability of success. Fine. The next thing is, next thing is variance of Poisson distribution. All right, variance of x is equals to, you must be aware of this formula by this time now. It is repeated at least 4 to 5 times here. Variance is e power x square, expectation of x square minus expectation x whole square. That means minus mu square. That means minus mean square. This mu is already obtained from the above discussion. It is just the matter of obtaining this thing e to the e expectation of x square, which is nothing but x square into p of x. Again, the simplification is up to you. When you simplify it, there will be some series. When you combine it, you will find that variance of Poisson distribution is again coming out to be lambda. So this is the distribution where mean is equals to lambda, and both are coming out to be, or mean is equals to lambda and variance is also equals to lambda. That means mean and variance are equal for Poisson distribution. How rare is that? It is again NP. So for a distribution, or if some quiz question is asked to you, which is the distribution where mean and variance are same, then you can quickly say that it is Poisson distribution. What is standard deviation? Standard deviation is nothing but under root of variance. I already told you, so it is coming out to be under root of lambda. Okay, mode of Poisson distribution. You just go through this mode part also. You will see that mode is coming out to be, the mode of Poisson distribution lies between lambda minus 1 and lambda. Okay, we will discuss some examples related to Poisson distribution in the next video lecture.